Shepard's lemma says that if you take the derivative of the expenditure function with respect to the price of one of the goods, then you'll get back that good's compensated demand function, or that good's Hicksian demand function. In this animation, we'll try to provide some intuition for why this Shepard's lemma works, and in the process we'll discover why it is that the expenditure function is concave in prices. The expenditure function tells us for any set of prices and any utility level how much income is going to be required for the consumer to be able to reach that utility level at those prices. So here we'll start with one indifference curve that corresponds to one particular utility level, UA. And we'll start with a particular set of prices, P1A and P2A, that form the least cost budget constraint that allows us to reach this utility level. The least cost bundle to reach this utility level at those prices is then the bundle A, which contains X1A of good 1 and X2A of good 2. The minimum that we have to spend to reach utility level UA at the prices P1A and P2A is then given by the expenditure function. All we have to do is multiply the prices by the least cost input bundle A. In other words, P1A times X1A plus P2A times X2A. What we spend on the first good plus what we spend on the second good together gives us how much spending we need to do in order to reach utility level UA by purchasing the least cost bundle A. Next, suppose that the price of good 1 increases to P1B. That means we'll get a steeper budget constraint, and in order to reach the indifference curve UA, we're going to want to buy a different bundle than the bundle A. The least cost way of reaching indifference curve UA will now be given by bundle B, where we buy X1B and X2B in order to reach the indifference curve UA. Similarly, we can think about what happens if the price of good 1 falls from P1A to P1C. We then get a shallower budget constraint, and again, we wouldn't want to purchase either bundle A or bundle B to reach utility level UA now if we're trying to do it in the least cost way. Instead, we want to purchase bundle C, which includes X1C and X2C, in order to reach utility level UA in the least cost way given the new price P1C. We can then think about how to translate information from panel A to panel B, where we have the price of good 1 on the horizontal axis and dollars on the vertical axis. What we'll do here is plot out a slice of the expenditure function that tells us for different P1 prices how much expenditure is necessary to reach utility level UA given the price of good 2 is P2A. We know, for instance, that it takes an expenditure level EA to get to bundle A when the initial price of good 1 is P1A. So for the price P1A, we can plot the point A' that corresponds to point A in panel A and label it as an expenditure of EA equal to P1A times X1A plus P2A times X2A. To see what the real expenditure function looks like, we're going to first draw a naive expenditure function, an expenditure function that doesn't allow the consumer to substitute away from goods that become relatively more expensive and towards goods that become relatively cheaper. In particular, we'll assume in our naive expenditure function that the consumer, no matter what happens to the price of good 1, will always purchase the bundle A. Her expenditure will therefore be equal to P2A times X2A, what she spends on good 2, which always stays the same given that we're holding the price of good 2 fixed, plus P1 times X1A. This would imply that her expenditure function was actually linear, with a vertical intercept of P2A times X2A, her spending on good 2, and the slope of x1a. Now suppose the price of P1 goes up from P1a to P1b. We know how much this consumer would spend on her naive expenditure function. We just look on the blue line and find what the expenditure level would be. But that assumes that she continues to buy bundle A. If we go over to panel A of the graph, it would mean that she'd be on a budget that has the slope of the magenta budget but goes through bundle A. In other words, a budget that has more expenditure than the actual magenta budget she'll choose at bundle B. Her true expenditure will therefore be below the blue line, below her naive expenditure that doesn't allow her to substitute. We can therefore put point B prime in panel B somewhere below the blue naive expenditure function. Similarly, we can ask what happens if the price falls from P1A to P1C. If the consumer was naive and simply didn't change her consumption pattern and continued to consume bundle A, we know her expenditure could be read off of the blue line, the naive expenditure function we've drawn. But that would imply that she's continuing to buy bundle A when really the expenditure minimizing bundle is bundle C. Her budget would then have the same slope as the green budget in panel A, but it would run through point A. In other words, it would be a budget with greater expenditure than what she actually needs to get to bundle C. Her true expenditure minimizing way of getting to utility level UA therefore involves less spending than the blue line indicates, and we can therefore put point C prime in panel B again below the blue naive expenditure function. Point C prime, A prime, and B prime all lie on the true expenditure function as opposed to the naive expenditure function that we've drawn in the blue line. Thus we can connect C prime, A prime, and B prime and estimate what the true expenditure function looks like. The expenditure function that holds fixed the price of good 2 and the utility level UA, and asks how much spending is necessary to get to utility level UA as the price of good 1 changes. Since the naive expenditure function, the blue line, is a line, and since the true expenditure function is tangent to that line but lies everywhere else below that line, we know that the true expenditure function must have this concave shape as the price of good 1 changes. We can also see what the derivative of the true expenditure function is at point A prime. The slope of the naive expenditure function is x1a. That's the derivative at point A prime. In other words, the slope x1a is equal to the derivative of the expenditure function. Or put differently, the compensated demand is equal to the derivative of the expenditure function with respect to price. That's of course exactly what Shepard's lemma says. We can conclude by asking what the role of substitution effects is in creating the shape for the true expenditure function. And we have our answer in panel B. The naive or blue expenditure function we've drawn is the expenditure function that assumes that the consumer will never substitute as prices change. In other words, it's the expenditure function for indifference curves that treat goods as perfect complements. Thus, as we take away any substitutability between the goods in people's tastes, we get a linear expenditure function in prices. As we introduce substitutability into the indifference curves, however, we will introduce an error in that naive expenditure function that will create the concavity of the true expenditure function. And the more substitutable the goods are, the more concave this true expenditure function will be in prices.